Welcome to pre-calculus.
We are starting with velocity. This is where we had left off. We've talked about velocity, or you've talked about velocity lots and lots of times. Velocity is basically how fast something is going. Normally, we first talking about average velocity. And average velocity is if you're going on a trip, if it's a 300-mile distance and it takes you, let's say, 3 hours to get there, then the total distance that you've traveled divided by the total time is your average velocity. So on average, this is how fast you were going during the trip. So it's the total change in distance divided by total time. The way we give the formula is this. You have f of b minus f of a over b minus a. And it's always in final minus initial. So f of b minus f of a. All right. Let's take a look at this one. A water balloon is propelled straight up using a launcher, so it's going up. The height of the balloon in feet, t seconds after it is launched, so the height is in feet, t is in seconds, and the height can be defined by this. So this is the height. It's 5 plus 65t minus 16t squared. And it says, what was the balloon's average velocity between t equals 1 and t equals 2? Average velocity is total distance divided by total time. So what we want is the distance at 2, right? And for that, we plug in 2. So 5 plus 65 times 2 minus 16 times 4. How much will that be? Um, 71. And now we want d of 1. That's the distance at 1 second. And that's 5 plus 65, which is 70 minus 16. How much is that? Right. Now, the average velocity is d of 2 minus d of 1 over 2 minus 1. So this is 54 minus 71 over 2 minus 1, which is just 1. What's 54 minus 71? Right.
Wait. You plugged in D2 before you put in D1.
Oh, sorry. 71 minus 54. So it's positive 17 feet per second. Right. Why does that make more sense?
Because you can't do something negative. There's no such thing as negative velocity. You can go backwards. That's negative. That's negative velocity.
So, velocity.
Small demonstration.
Okay, velocity is a vector quantity, meaning it's got a magnitude and a direction. So the actual number is the speed. So if there was a speedometer on this thing, it would read 17 feet per second. The sign, whether it's plus or minus, is the direction. So if it's positive 17, that means it's going in the positive direction. Now, in this case, the problem is a water balloon propelled straight up. Okay? If it's propelled straight up, it's going up. Up is always the positive direction. So if this were going down at 17 feet per second, it would be negative 17. Okay. That's average velocity. It's, on average, how much was your velocity? The instantaneous velocity is if you're in your car and you happen to look at the speedometer, at that specific point, what your speed is or what your velocity is your instantaneous velocity. It is the velocity of an object at a specific point in time. In other words, it is the rate of change or the slope of a function at a specific point. So for instantaneous velocity, we want to find the instantaneous rate of change. And what we're going to do is use the same formula as we were before. And now our variables are t, because we have time when we're talking about velocity. So it's f of t or v of t and so on. A window washer accidentally drops his lunch off his scaffold 1,400 feet above the ground. So the lunch is now going in what direction? Down. It's falling. The position of the lunch in relation to the ground is given as this, where time t is given in seconds and the position of the lunch is given in feet. Find the instantaneous velocity of the lunch at 7 seconds. All right. So for this, we need d of t plus h, which is going to be 1,400 minus 16 t plus h squared. So this is 1,400 minus 16 t squared minus 32 th minus 16 h squared. I squared and distributed the negative 16 all in one step. Okay? Now, the instantaneous velocity at any given time is going to be given by d of d plus h minus d of t over h. Ooh, and this is the limit as h approaches 0. T. So this is what we just found, d of t plus h. Now, minus d of t, which is what? What's d of t? 1,400, right, plus 16t squared, all over h. No, because you're subtracting and you distribute. Okay? All right. So now I'm going to cancel the 1,400 with the 1,400 and the 16t squared with the 16t squared. This is the limit as h approaches 0 of this, which means this is the limit as h approaches 0. Now look, I'm going to do a little bit more multitasking, but I will change colors. I'm going to cancel out one h from each term. So here the h goes away. Here one of the h's go away and the bottom h goes away. So finally this is negative 32t minus 16h. So v of t is negative 32t. That's the instantaneous velocity at any given time. What we want now is the instantaneous velocity at 7 seconds. So what I want is v of 7, which is negative 32 times 7, which is negative 224 feet per second. And the lunch is going down, right? The lunch is going downward. So the velocity has a negative in front of it. Now, if you look at this equation, this was when the lunch was just falling straight down, right? Do you see how that equation looks? And this is when something was shot straight up. What do you notice? Is there anything in common between the two? Negative 16t squared appears here. Negative 16t squared appears here. Now, in the case of something being launched up, right? If you have a ball, you throw up a ball, it goes up, and then what's going to happen to it? It's going to go back down. Now, this one is just going back down with the lunge. So, what is it? It's gravity, negative 16, right? It's the acceleration due to gravity, right? How do you know acceleration due to gravity? It's 9.8 times 9.8 meters per second squared, right? In feet, that will translate to your negative 16t squared. Okay? Yeah. No.
I heard that
If
How's that possible? Where are the higher elevations?
okay, so in this problem, the distance in feet of a water rocket from the ground after t seconds is given by this same situation. Find the instantaneous velocity at any time t. Okay? At any time t. So, what are we going to find here? We need v of t. Right. V of t is going to be s of t plus h minus s of t over h. Ooh, this is the limit as h approaches 0. Yes? I know. All right, so s of t plus h is 90t plus 90h minus 16t plus h squared. So 90t plus 90h minus 16t squared minus 32th plus 16h squared. Minus, sorry. Okay. When we plug this in, we get that the limit as h approaches, that this is the limit as h approaches 0 of what we just found. Now, minus s of t, so we get minus 90t plus 16t squared all over h. And these are going to cancel. The 90t and the 16t squared will cancel. And can I cancel out h's? One from here, one from here, one from there, and one from there. So this is the limit as h approaches 0 of 90 minus 32th minus 16. Is it? Oh, I didn't take one. Oh, I didn't cross that one out. Sorry. Minus 32t. Therefore, v of t is right. That means, okay, this is the v of t. So the velocity keeps changing. Does that make sense that the velocity is changing when something is falling?
Yeah, force obstructs it.
Because why? Well, because acceleration due to gravity is pulling it down, right? So it's accelerating. So if you're holding something up in the air, the velocity is 0 if you're just holding onto it. Now, the minute you let it go, the earth starts pulling it down. And every second, the velocity increases. So 9.8 meters per second, and then times 2, and then times 3, and then times 4, and then times 5. So at every second, the velocity is a little bit more. So this is the general expression for the velocity at any given time. And let's say you were curious to see what would the velocity be at 2 seconds. What would you do? Plug in 2. Here, given this function, you want to find the average velocity. So this is the function of the distance of something, and you want to find the average velocity, right? So for average velocity, we're going to do f of 5, and we're going to find f of 1, and v average is going to be f of 5 minus f of 1 over 5 minus 1. Okay, final minus initial over the delta t. So f of 5 is 3 times 25, 75. F of 1 is just 3 times 1, 3. The average velocity is 75 minus 3 over 4. So 72 over 4 is what? 18. Now, if you're not given units specifically, you don't have to put units, but if you are given units somewhere in the problem and you leave them out, then that's wrong. Now it wants you to find the instantaneous velocity at 4 seconds. They didn't give you the units for the distance. Now, the instantaneous velocity at 4 seconds means I need f of t plus h. So that's 3x plus h squared. So the v of t is going to be 3x squared. All right, 3x squared plus 6xh plus 3h squared minus, how much is it? 3x squared. Let's be consistent. This is supposed to be an x. So v is the limit as h approaches 0 over h. The 3x squares will go away, and I can cancel out an h. 1, 2, 3. So the speed, or the velocity, is going to be 6x. That's it. Just 6x. Huh? Oh, it's at 4 seconds. Yes, v of 4 is 24. All right? Okay, one last one.
Is this the last example, Paul? We're going to do material for this year?
No.
That's so easy.
An object is thrown straight down, and look, 16t squared. The total distance y the object falls can be modeled by this. So y is the total distance. It's also, you can also say it's the change in the distance. It's the change in the position.
Wait, so it's trying to model
And
not
it's,
only gravity, but how far you threw it?
okay, and it's equal to 16t squared plus v naught t. Okay? Now let's think about this for a minute. If I have a ball, and I'm just holding on to it, and it's at rest, and I just let it go. Imagine that. Now imagine I have a ball, and I throw it down. Which one's going to get down fast? Which one's going to reach the... When I throw it, it's going to reach the ground faster. So the initial velocity with which this is, the problem starts makes a difference. And that's why it factors into our equation. So v naught t, v naught is the initial velocity with which it was thrown. Now, if you simply let go of it, then what was the initial velocity? 0. So that part will fall out of the equation. Okay? So v naught is measured in feet per second. If an object is thrown straight down from a height of 816, it's thrown straight down. It takes 6 seconds, so this is the height, and it takes 6 seconds to hit the ground. What was the initial velocity of the object? All right? So it's thrown from a height of 816 feet. So here's the ground, and it was thrown from there. So my equation is this: y equals 16t squared plus v naught t. Now I said y is the change in the position, right? Or it's the total distance that this thing traveled. How far did it travel by the time it hit the ground? 816. So we have that 816 is equal to 16 and t is 6 seconds, plus v naught times 6. Right, we're going to solve this for v naught, and we're going to get that v naught is negative 40 feet per second. And it is being thrown down, so it does have to have a negative in front.
This equation is really accounting for like wind drag and stuff like
Okay, please let's go into like all of that stuff later. Let me focus on this now. Okay. Now, what was the average velocity of the object? For the average velocity, what I need is the initial position, the final position, and the total time. So the final position is y of b, and the initial position is y of a. Okay? Now, initially, what's the time initially? 0. So here it's y of 0, because time is 0, and that is going to equal what?
Just 0.
0. Wait a minute.
That makes sense. But you draw some ball in 0 seconds. Actually, that's 0 velocity.
All right, so let's take that one more time. So basically, for the average velocity, what we want is the total distance divided by the total time. How much did this thing travel? It traveled 816 feet, right? So basically, the initial position was at 816 feet, and the final position is at 0. So V average is 0 minus 816 over the 6 seconds, and that gives us 136, negative 136 feet per second. All right? And it is negative because, again, it's moving downward. Next, what was the object's velocity when it hit the ground?
Isn't that just a trick question? Would it be 0 when it hits the
No.
ground?
After it hits the ground, yes, but as it's going further and further down, the velocity is increasing and increasing and increasing. It is at its highest velocity before it hits the ground. That's why it hurts so much, because you've got so much velocity. That squared times your mass is your energy. That's why it hurts so much when you fall. And the higher up you fall from, the more it'll hurt, because you've accumulated more of a velocity. So the object's velocity when it hit the ground, basically what I want is the velocity at t equals 6. So I want the velocity at t equals 6. That means, what was my position function? 16t squared plus v naught t. Okay? No. We need to find, this is y, we need to find v. So we need to do the limit as h approaches 0 of y of t plus h minus y of t over h. As h approaches 0, and then we're going to plug in 6. So remember we did f of t plus h all the time? That's what we're doing now. Because we want the instantaneous velocity at t equals 6. That's what we want now. We want the instantaneous velocity at t equals 6. So this is t squared plus 16th plus 16h squared plus
Yeah, isn't it 32T?
plus V naught T plus V naught H. 32. Plus 32. So basically, this is the limit as H approaches 0 of 16T squared plus 32TH plus 16H squared plus V naught T plus V naught H minus 16T squared minus V naught T all over H. And now the 16T squares will go away, and so will the V naught T's. And if I can cancel out an H, 1 here, 2, 3, 4 of them, the limit as H approaches 0, so V of T is going to be 32T plus V naught. No, because the H is going to be 0. So what I have left is the 32T and the 16H and the V naught. So that's what I have. So V at 6 is 32 times 6 plus, what was the initial velocity that we found at the very beginning? 40, negative 40. So this is going to be 32 times 6 minus 40, 152. Right, feet per second. All right, so that homework will be due tomorrow.
So why isn't it negative?
Yeah, that's